All right. How's it going, guys? So I kind of reached out to Sarah yesterday to query to see if people wanted to Zoom or not, but I think the fear was that the internet with all of you trying to jump on and Zoom at that time would probably not work. So I'm going to continue down this road of recording and we'll just kind of, you know, figure it out as we go. All right. So we are going to find some volume and this is going to start to look crazy, but sometimes calculus looks crazy and it's really it's not terrible. And I know I say that a lot, but really this will visually will look hard, but it's a really simple concept. So this is hard to do when I'm not in front of you guys, but look, that is a piece of yellow paper. And we could find the area of that guy. It's like two-dimensional. In theory, it's got some thickness, but we'll just consider it as 2D. Okay, well, how do you get three dimensions from two dimensions or volume? Well, one of the ways is just what if I had like 100 of these guys and I stacked them together? Now we have volume. And so all we have to do to get volume is to add up a bunch of two dimensional areas. And so in calculus, right, to get volume, you just have to integrate, which is fancy for add things up. Add up what? A bunch of these guys, right? So if I can find the area of this yellow paper and I just add them all up, that's going to be the volume. Going back to geometry, right? I mean, you guys remember length, right? Down here, length times width. Well, if you add volume in, it's length times width times height. You just have that extra dimension that you multiply by. Okay, so we're going to be finding volumes of discs using disc. That's fancy for circles. Okay, and washers. And so up here, a disc is a solid circle, and a washer is a circle, but it has a little hole in the middle. If you've ever built with things, you have a bolt that goes through there, and you have lock washers and other stuff like that. Okay, so we're just going to start with with this disc method, and again, the disc method is a circle. And going back to geometry, what is the area of a circle? It's pi r squared. Very simple, right? So if the area is pi r squared, the volume by definition, right there, it's the integral of the area. So I integrate pi r squared. But this pi is just a number. And what do you know with numbers? They can come out in front. And so you bring the pi out in front and you just have pi times the integral of r squared, which is that guy. Okay. So simple stuff. So all we're going to have to do, and this is the game changer right here, is we just need r. If we could just find whatever this radius is going to be, we just evaluate the integral like we integrate everything else. Okay. So let's check out and see what they're having us do. Find the volume of the solid bounded by the curve y equals square root of x. So I'm going to overdraw here, you guys, and then I'm going to hopefully at the end I'll pull it together and show you what I want you to draw, because I don't want you to draw these complicated things every time. But the very first time we're going to get a visual in our brain. So we have the square root of x function, which we know looks like that. The x-axis, which is right here. The line x equals 4, which would be this line. So we're just going to draw that in. Okay. Revolved around the x-axis. What the heck does that mean? All right, this is where your mind's going to be like, Carpenter, what? It's too early for this. I know. This is a two-dimensional piece. But what's going to happen is I'm going to spin this guy. You got to draw in your spinny guy. That's my spinny guy, and you got to call it a spinny guy, and you got to draw the spinny guy because the spinny guy is really, really important. It says revolved around the x-axis, so you draw your spinny guy around the axis of rotation, which is that. What the heck does that mean? That means that this piece, you guys, is going to come out of the paper, right? It's out of the paper and it's spinning, and it landed down here, right? It's mirrored down here, and it's spinning. Okay. And so now you can see it kind of looks like a ham or something, right? When you take a two-dimensional piece and you spin it, you're getting this solid, right? That's a three-dimensional picture. And you guys, all we're going to do is we're going to add up a bunch of circles. Yeah. That's what we're going to do. We're going to use discs because it looks like this. It looks like circles would fill that thing up. And so really, I'm going to find the volume by just doing pi times the integral of r squared. Okay. Because pi r squared is the area of each individual circle, and an integration sign is a summation, right, of all of those things. Okay. So I do not want you guys on the AP exam and on homework to draw this complicated thing. All right. All I want you guys to do is to get the region for sure, which is the square root of x, the line x equals 4, and the x-axis. So all you want is the two-dimensional. The next thing you do is it says revolved around the x-axis. You have to draw the spinny guy. The spinny guy is super important. I'm kind of freaking out because I don't have like a red pen or something. I always have a red pen. Hold on. I don't know if I told you guys, but both Taylor and Kennedy now have COVID too, so we're chilling. All right. You draw your two-dimensional region, and you have to draw the spinny guy. And I really focus on that. I know it sounds annoying, but it's super important because the last step is to find R. That's all we need, right? So this is clearly important. R is always going to be the distance from the axis of rotation, which is wherever you drew your spinny guy, to the other end of the region. So you draw across it and you label R. And then I'm going to come right over here. I'm going to say, well, what's R? Okay. R is the length of a line segment. The length of any line segment is always going to be the top function minus the bottom function. If it was horizontal, it would be right minus left. So this line segment is always the top minus the bottom. Feeling like we should pause on that. What does that mean? Well, if you have a function here, and this guy is up at the point 210, okay? And then you have another function right here. I want to know what's the length of that line segment. Well, if that's the point 26, you guys would tell me, hey, I know how long that is. That is, I'm going from 6 up to 10, so that's 4. Exactly. And how did you get that? You took the top and you subtracted the bottom. Okay, in this case, they're just numbers, but that always works. The length of any line segment on your graph is going to be top minus bottom. Okay, hopefully that's enough to convince you. You're going to write top minus bottom. Well, this is y equals the square root of x, and this is the line y equals 0. So top minus bottom is root x minus 0, which is clearly just the square root of x. Okay, and on all these problems, you guys, once you find r, you're home free because the volume is equal to pi times the integral of r, which we now know is square root of x squared. Okay, this is dx, and these are all x's. Whenever you do top minus bottom, everything is x's, just like when we were finding area. So from where to where? Well, it starts right there at 0, and it goes over there to 4. Okay, and we can do this one. This is just pi, integral 0 to 4. Root x squared is just x. I haven't integrated yet. Equals, now let's integrate. I know I've got this pi thing. And when I integrate x, I get x squared over 2, evaluated from 0 to 4. So I have pi times, I plug in, I get 16 over 2 minus 0, which is just 8 pi. Okay, so what you guys just did is you said, hey, the volume of that thing is 8 pi. And it's crazy, right? You're taking a region and you're spinning it around something. And when you spin it, it gets a third dimension. But when you look at what you made, you could clearly just add up a bunch of circles. And the radius at any point is going to be root x minus 0. So when you plug that guy in and you evaluate, you're good to go. Obviously, we're going to practice more of these. Okay? It's the procedure, you guys. Trust me, if you want to succeed at this, you draw your two dimensions. You draw your spinny guy. Super important, because the spinny guy tells you how to draw R. You start on the spinny guy axis and you go to the other end of your region, and you look at your line segment. It's top minus bottom. So I write top minus bottom. Okay, let's do it again. All right, find the volume of a solid bounded by the curve y equals x squared. So I'm going to draw this guy in. Y equals x squared, the x-axis, x is 0 and x is 3. So all four of those things gives you, that's y equals x squared. The line x equals 0 is a vertical line right here. The line x equals 3 is a vertical line right here at 3. And the x-axis is right here. So I have my region. Yeah. And then we're going to revolve it or spin it around the x-axis. Spinny guy, super important. Spinny guy tells you where to start your radius. Your radius starts on the axis that you drew your spinny guy. Over to the other side of the region, label it R. Come over here and tell me what R equals. R is super easy. It's either top minus bottom or it's right minus left. Clearly, it's top minus bottom. The top function is x squared. And the bottom function is the line y equals 0. So r is x squared minus 0, which is just x squared. Once you have r, right, you have your volume is equal to pi integral from 0 to 3 of r, which is x squared squared with respect to x, equals pi integral 0 to 3 x to the fourth with respect to x. And then we're going to get pi. You're going to do x to the fifth over 5 from 0 to 3. And then when I plug in 3, I get 3 to the fifth over 5 minus 0. I don't even know what that is. I got 9 and 9. That'd be 4 of them, right? That's 81 times another 3. 81 times 3 is 240. What? 243? 243 pi over 5? I don't know. You know the best part, guys. I'm just going to start claiming COVID brain, even if it's not a thing. I don't know. If I'm wrong, it's not me. Cool. Okay. All right. So let me give you a visual of what just happened, because it's early, right? You're just learning this. You don't want to do these complicated drawings. But what we did is we took this region right here and we spun it around the x-axis. And when you guys do that, this whole thing comes out of the paper and starts getting reflected and spun down here, right? And spinning around. It looks like a big horn now, right? And now you can see that all we did is we added up a bunch of pi r squareds, which gives us a three-dimensional figure. Okay. All right. I'm a little nervous, you guys, because the title of this is Discs and Washers, and I don't really know that I want to go into the washers yet. So let's do this example and see if it jumps into washers. And if it does, I'll probably save that and we'll do washers tomorrow. But it's good to know what the heck, what's the difference. All right, so let's check out this region. We've got the square root of x, which we're real comfortable with. It looks like that. The y-axis, okay, so now we're using the y-axis. The line y equals 4, which is horizontal up here, revolved around the y-axis, spinny guy. So this is not a washer, so this is good. We're still on discs. Okay, what changed is that spinny guy thing, right? That's totally different. Now I'm going around the y. So now I'm not going to, well, I'll draw it over here. If I drew this for you, we don't want to make these complicated drawings. But if you did, it'd be reflected backwards, right? And spinning this way now. So now you kind of have that same horn that we just did, except it's opening up, right? So you have all of these circles that you're going to find the volume of. Okay, if you look at the pictures, it's complicated. If you follow my steps, you'll never go wrong, right? You just follow exactly what I told you. Draw your region. Good. Told me to spin it around the y-axis. I drew my spinny guy. That's super important because your radius starts at the spinny guy and goes across the region to the other part of your function. And then that's r. Cool. It's a line segment. It's always either going to be top minus bottom, or in this case, right minus left. Guys, right minus left. Now, everything has to be in terms of y's. Top minus bottom, everything here is x's. X equals 0, x equals 3, x squared, dx. As soon as you get a line segment that you labeled because you followed the rules, that's going to be right minus left, which is everything's going to be in y's. So I'm going to write r equals right minus left. You guys know that this formula is y equals the square root of x. But if I need to write it in terms of y's, you got to solve this guy for x. So if you square both sides, that's the same thing, right? And this is the line x equals 0, right? So we have x equals y squared and we have x equals 0. Right minus left, y squared minus 0. Okay? And so that's the same as just y squared. You're home free. Your volume is pi integral r, which is y squared squared with respect to y. How come? Because everything y's. How come everything is in y's? Because you're doing right minus left. You guys should like rewatch this video. There's so many things, you guys, that will just become repetitive and easy. As soon as you see right minus left, everything's y's, which means these values on your integral bounds have to be in terms of y. So you're going down from this lowest y value of 0 up to this highest y value of 4. And so you get pi integral 0 to 4 of y to the fourth dy. Okay, very similar to what we just did above, right? Except we're going to 4, not to 3. But the math is real similar. So you have pi, you integrate, you get y to the fifth over 5 from 0 to 4. You plug in 4 to the fifth over 5 minus 0 to the fifth over 5 are just 0. And I'm going to cheat here. 4 to the fifth is 1024. So 1024 pi over 5. Okay. Cool. All right. I'm guessing that, oh, I lied, you guys. Perfect. Tomorrow is also labeled discs and washers. Tomorrow would be all washers. Okay. All right. So I'm probably just going to set this one up for you and then and let you guys math 9 it or something. But let's practice those steps one last time, and then you're off and running. Find the volume bounded by the curve. Here we go. Y equals x squared. That's that guy. The y-axis. That's this guy. The line y equals 3. That's that guy. And you're going to spin it around the y-axis. Now you're going this way. And that was up there at 3. Okay, so draw your region that's enclosed by all of those functions. And then you take your red pen in your brain and you always start on your spinny guy axis and you go across the region. You label it R. You say, okay, let's go find R. What is R? R is always top minus bottom or right minus left. It's right minus left. Okay, this is the function y equals x squared. But if I'm doing right minus left, I have to say it's in terms of y. So you have to solve that for x to get x equals the square root of y. This is the line x equals 0. It's a vertical line. It's also the y-axis, but the y-axis is the function x equals 0. So right minus left would be root y minus 0, which is just root y. You're home free. Your volume is pi. Why is there a pi there? You guys, there's pi's there because we're spinning this and we're getting circles. Pi's don't come out later on when they're not circles. Okay, so just remember that. Pi integral from 0 to 3, low to high, of r, which is root y, squared, dy. Okay. Math 9, that bad boy. Maybe you get a decimal for a change, round it to 3, and you guys are off and running. Okay, a little visual here just to kind of set you guys up. What happens? What's up with this washer thing? Well, let's take that region, but let's spin it around this guy. Whoa. We're going to make like a nasty fruitcake. You spin it around here. Yeah, this guy's coming way over here. And you got this big hole in the middle. And you're spinning it around, but check it out right there. Oh, dang. You've got a washer. The only difference, you guys, is that there's 2 R's, whatever. Anyways, hope you guys are doing good. I'm super bummed I'm not back. But, what are you going to do? All right, keep it real.